Hello and welcome back to Textile Build. So thanks so much again for joining us today for our third live Textile Build training session. Similar to last time, for those of you who are joining us live, please note that there are multiple ways to ask questions and interact with the Textile Build team during the live session. You can use the link at the top of the screen here. You can join our Slack channel, or you can actually click on the icons on this initial slide if you are joining us and following along with the slides. Update those links, if you will. Most people don't seem to be using these Q&A links anyway, so you're probably better off just sticking to the Slack channel if you have any questions there. So here is the basic structure that we're going to cover today. We're going to spend a little bit of time at the beginning exploring some fun IPFS P2P features and things like that. But most of today's session is going to be spent on slightly less structured code exploration. And we'll do an initial sort of update to our Đapp, where we use a slightly different design pattern for actually making things work. And then we'll jump into a much more complicated example, and I'll go through the code with you sort of line by line so you get an idea of what's exactly is going on. So as always, we're going to be pretty hands-on right from the start. So to start with, make sure that you have your IPFS daemon running locally. And in fact, you're going to need this daemon running locally for sure when we start doing our coding exercise at the end of this, or towards the end of this session. So make sure your terminal is up and running and that your copy and paste skills are primed and ready to go, because we're going to be running a bunch of different commands and playing around with some code. So without much further ado, let's get started. So in previous sessions, I've talked a lot about IPFS nodes or peers interacting with each other on the IPFS network. But I haven't really totally defined what we mean by that when we make these types of statements. So for instance, what types of interactions are peers engaging in? How do they actually exchange information? To what extent do they advertise what they actually have, and how do they request new content? All of these types of things are critical when peers are communicating over a decentralized web. So we're going to build up a bit of an intuition for that today. Now, we have seen a few of these interactions before, like when we query the distributed hash table, or DHT, to find out the location of a peer or a particular piece of content. But there are also a couple of other mechanisms that we're going to talk about a bit today, including something called bit swap and a little bit about a messaging protocol that IPFS uses more recently. So what we do know is that peers on IPFS use their peer ID to identify each other, and that this peer ID is based on the hash of their public RSA key, right, from their public key pairs. So they've got a private and a public key, and their peer ID is based on their public key. We also know that distributed hash tables are used to find or query peers by their peer ID and content by its content ID on the IPFS network, and that we can get and add content to the network as IPLD DAG structured objects. So basically hierarchically linked tree of data, or more properly a DAG, directed acyclic graph. So the next step is to cover actually how is the content retrieved and requested among those peers. So we know what they're looking for and how they look for it, but then once they've done that, how do they actually exchange that information? So that brings us to the topic of something called bit swap. So you may have heard, probably from me in previous sessions actually, IPFS compared to something like a BitTorrent mixed with Git, mixed with other technologies, or something to that effect. So this BitTorrent piece comes from essentially how blocks of data or chunks of data are exchanged and requested over the IPFS network. So IPFS actually does things a little bit differently than BitTorrent. So they have their own specific exchange protocol which is called BitSwap. And BitSwap is essentially the data trading module for IPFS. Okay? Its primary purpose is to request blocks from and send blocks to or among peers in the network. And that's pretty much all it's for. It's actually a pretty simple protocol, and we'll talk about that in a second. So BitSwap itself has two primary jobs. Attempt to acquire blocks from the network that have been requested by the local client peer. And in addition, or with this, to judiciously, but also very strategically, and we'll talk about that very briefly in a second, send blocks of data that it already has in its possession to other peers who want those blocks. Okay, so this idea of BitSwap it's a good name, where essentially these peers operating on this network are swapping bits of information or bits of data among each other based on who has what and who wants what. So the way it works is relatively straightforward, and it's based on this pretty simple message-based protocol where all messages contain want lists, so the list of blocks that the peer wants, and actual blocks of data. So when responding to a want request, the actual data that would satisfy that request. Essentially, when a peer receives a want list from a fellow peer, that peer needs to decide if they want to send over the requested blocks. And obviously, it checks if it has them first. If it doesn't, then it's really not much of a problem. And then the other peer, upon receiving those blocks, needs to then send out a cancel notification telling the network that they don't need a given block anymore because they've retrieved it. This sounds pretty straightforward, right? You're just telling things what you want and telling things when you have it and telling things that you do have it. But there's a lot of complexity baked into this protocol and how it works. And even now, it's still pretty much a work in progress, like a lot of projects or pieces of IPFS. So the message-based protocol is relatively simple. It could change in the future, but that won't change how BitSwap essentially from an abstract level works. So if you recall from our last session, when we add content to IPFS, it actually gets chunked up into a bunch of small blocks of data. And you might remember I mentioned it was about 256K for each block. For small files, obviously no chunking or blocking needs to happen. But for large files, this can get split up into a bunch of tiny pieces. So these chunks or blocks are what get shared with BitSwap. So when you're interacting with IPFS at a very high level, you're requesting for entire files. But what's actually happening at a low level is that the swarm of peers that you're connected to is exchanging these little blocks, these 256K blocks of data. Now, the key difference here from, say, something like BitTorrent is that unlike in BitTorrent, where blocks are being exchanged from a single torrent, so usually like a single file, a video, or something like that, all the peers that happen to have or are hosting that particular file, seeding in the BitTorrent world, they're exchanging bits based on the data from that particular file. On IPFS, we basically have just one giant swarm or multiple very large swarms. IPFS can support that as well, so that peers can just pull blocks from just about anyone who happens to have that particular file. And this fits into the whole kind of structure of IPFS as the interplanetary file system. We've got this singular file system that all computers are connected to and that all computers can use to share information. And I actually shouldn't say computers, I should say devices, because the idea is it's much more generic than the idea of a computer necessarily specifically. Right. So the structure of the IPFS network and in fact the distributed hash table that we have is used to make all this sort of interacting between peers possible. Now, on top of all of this, we actually have a pretty complex dance among peers when we're exchanging blocks. And this block exchange is essentially modeled as a marketplace for data exchange or data bartering. And each peer that is participating in this marketplace, this BitSwap marketplace, has some internal strategy, just like humans interacting in a marketplace, that they use to decide if they will exchange content or whatever with any other peer that they are connected to. And these strategies aren't necessarily fixed. And they can be designed to do things like incentivize data duplication or uptime, or punish leechers on the network, so peers that aren't providing content but are only just requesting content, or whatever sort of strategy they want to use. And the BitSwap protocol has this sort of dynamic, or the ability to swap in different strategies baked right in to the protocol. So in fact, in the future, the IPFS network will likely support a whole range of arbitrary strategies. It could be based on a bartering system based on a virtual currency, like Filecoin, for instance. And so that's a nice little interlude to the next slide. But here's just a reminder of what we're essentially talking about here, right? We're talking about exchanging the blocked content, or content that's been blocked up into small bits. So in this case, from our previous example, we may have had a large file that gets split up into tiny pieces, and these tiny pieces are what get exchanged in BitSwap. So this brings us to our first aside for the session, which is Filecoin. So I'm only going to briefly talk about Filecoin, but I'll provide some resources and links at the end of the slides for you to check out as well. So if you aren't already aware of Filecoin, this is basically Protocol Labs, which is the group behind IPFS, the group that started it. It's their crypto coin. So the Filecoin system is essentially, well, not essentially, it is a decentralized market for taking advantage of unused hard drive storage space. And their ICO already came and went, so you're a little too late to get on that. But they are quickly moving towards a working test net, so that developers can actually start testing applications on top of this decentralized storage system. So the basic idea here is that Filecoin is going to let just about anyone participate as a storage provider, rather than just folks like Dropbox or Amazon or these large Web 2 companies. So essentially, you've got a couple of hard drives hanging around your apartment, and you've got a pretty decent internet connection. Well, then you might as well take advantage of that and start earning some Filecoin, which you can then exchange on some crypto exchange for US dollars or Bitcoin or whatever else you might want. The other thing that it will do, or it's proposed to do, is allow miners to compete on things other than just cost or proof of work, like reputation, data availability, things like that. And I'll talk very briefly about that in a second. But essentially, once Filecoin is up and running, it's going to do a couple of important things for web-based storage. The most important being that it's going to be designed to incentivize things like end-to-end encryption, erasure coding, uptime, replication, and things like that we kind of already pay a little bit extra for when we're using some sort of cloud-based file storage. The IPFS network will incentivize these types of practices. But maybe more importantly than that, the folks behind Filecoin are also hoping it will lead to increased competition for storage space. And so hopefully everybody will benefit in this type of market-driven system, where if we've got enough storage on the network, the price of storage will go down. And there are lots of different economic models that Filecoin folks have been exploring. It'll be very interesting to see how that shakes out over the next couple of years. But essentially, Filecoin relies on two proofs like most other crypto coin systems. Although some of them rely just on one primary proof, but Filecoin is kind of based around two ideas. So unlike Bitcoin, whose proof of work protocol kind of just wastes energy, you just have to prove that you've solved a bunch of cryptographically difficult calculations. Something like proof of replication will actually be used to accomplish something useful, which is prove that your data is safely stored somewhere and is accessible. So proof of replication, that gets used to prove that any replica of data is stored in physically independent storage, right? So in other words, that someone has actually stored your data for real in a real place somewhere, and that you can actually go and get that data back if you need it, right? Wouldn't be very good if you were paying the network to store your data, and then it just disappeared. So we need some proof that it's actually there and available. Then the second piece of this is proof of space-time, right? So we want to be able to prove that there's storage space for your data, or your data is being stored, but also that it's being stored when you're paying for it. So proof of space-time bounding is actually used to prove that some data was being stored throughout a period of time. So for instance, if you're paying the network to keep your photos backed up for you, you want to be sure that they've been storing those photos the whole time that you were paying for them, and not just periodically or not at all. So proof of replication and proof of space-time allow the Filecoin system to essentially run this storage market and then prove that storage is actually happening. Now, obviously, one slide isn't enough to explain a very complex game theoretic-based marketplace for buying and selling digital storage, but hopefully that gives you a kind of brief idea of what's going on here and gives you an idea of some of the motivation behind IPFS. But really, you should probably just watch this video on Filecoin, which gives a much better picture of how IPFS and Filecoin fit in together on the decentralized web. So watch that one after our session here today, and that should give you a better idea of exactly what's going on. Okay. All right. So I'm going to take. Actually, we'll keep going, and we'll stop for questions in a little bit. So what's actually happening here is that Bitswap, and the ideas around a data marketplace exchange were actually presented in the original IPFS white paper, which I also strongly recommend you check out, by the way. And I've put a link at the end of the talk to the IPFS white paper, but also to a series on demystifying this white paper a little bit. So there's a series of blog posts that kind of dig in a nice, friendly way to what's actually being talked about in the IPFS white paper. But anyway, this is a pretty big piece of the IPFS puzzle, and this is just an excerpt from that white paper where it says the DHT and Bitswap allow IPFS to form a massive peer-to-peer system for storing and distributing blocks quickly and robustly. So obviously, this is a sort of key piece of all that. So we're going to kind of explore these protocols a little bit more from some examples. So just a quick refresher. You might recall from a previous session that the distributed hash table, or DHT, that IPFS uses is essentially the routing layer for IPFS. So it's a distributed key value store that allows IPFS peers to locate peers and content on IPFS. And so its primary purpose is to announce that a node has some particular data or content, or find out which nodes have some specific data or content that the peer wants. In this case, it's via its content ID or multi-hash. And then if the data is pretty small, so less than 1 kilobyte, we can actually store this data as a value directly in the distributed hash table. So instead of having to say, I'm looking for this content, who has it, if it's small enough content, we can just say, I'm looking for this content, and thank you very much. For larger values, which is pretty much everything else, sort of more common things, we actually just store a reference to the data. And in the case of IPFS, we store the peer IDs of the nodes who can actually serve up the content. So this is a pretty simple idea, right? We've got this DHT, all the keys are content IDs, and the values are the peers that can serve that up. Now, just a reminder, you can actually explore the distributed hash table directly to get an intuition for how this works. And so normally you don't need to run these commands, but when you use the higher level API like add, cat, get, etc., you're actually querying and informing the DHT automatically that you have data or that you're looking for data. But as always, it's good to know what's going on under the hood. So do feel free to play around with this stuff. Just keep in mind that sometimes these commands can be quite slow when run on their own like this, especially if you aren't connected to many peers, obviously, or you're not directly connected to a peer that actually is able to provide some particular content. So you can run these commands, and most or all of the DHT-based commands are prefaced with DHT. So we have IPFS DHT provide, and that will allow us to tell the IPFS network that we actually have specific content, in this case, a specific block that we want to tell the DHT we can provide. We can also, so that's sort of like adding to the DHT, and then we can also ask peers who have a particular piece of content. So we could say IPFS DHT find providers or find provs of a particular piece of content. Or we can even, and this happens to be the sort of classic cat photo that we've been using in examples and things over the last 2 sessions. And then to actually find the location of a peer based on their network address, we can use IPFS DHT find peer to actually locate a particular peer. And this one right here happens to be my peer that we have on the network for some textile-based work. You can query that peer and find out where it's actually located. All right. So that's some DHT stuff. What about bit swap? So we're going to actually play around. We've already played with some of the DHT commands, so we'll play around with some bit swap commands today to get an intuition for that. And as always, there is a command for that, in particular for the second piece of the IPFS puzzle. So to see it in action, we'll kind of have to be in the middle of a data exchange request dance, if you will. So what we'll do is we can request a very large file, and then we can see what's happening while the bits are being swapped and the downloads are happening in the background. So first things first, you're going to start by just getting an idea of what your peer is looking for right now. So we're going to query our bit swap want list. And right now, this should be empty because we aren't in the middle of requesting anything. And then we'll go ahead and change that in a second. So first, let's just try something here. So we've got IPFS bit swap want list. And mine doesn't return anything because essentially my want list right now is empty. All right. Now, if you go back to our slides here, oops, what we're going to do is open another terminal, which you see I already had open there, and we're going to request or get a very large file. Now, in this case, we're going to grab the classic big buck bunny video, which is a open source video, and you can actually stream it over IPFS at the link provided at the end of these slides, so that you can see that I'm not having you download some weird video file or anything like that. Oops. And what we'll do is we'll get that file, and we'll then query our want list, and you'll be able to see that in the background your peer is requesting various blocks associated with that file. So what you want to do is open up another terminal if possible, and we'll actually grab that particular large file. So I'm just going to copy and paste that file. All right, and we'll do it on a separate terminal here. So I'm going to go ahead and go IPFS get. Now I already have this file, so mine might go quite quickly. Hopefully yours will go a little bit longer, and you can actually query your want list of it. So as that's going, mine is almost instantaneous. But what you should do is while it's downloading, go IPFS bit swap want list, and you'll see that various different values crop up. And what I can do is I'll share my want list from a previous run at the end of this session, so that you can see what that looked like if it wasn't working for you. But essentially, what you'll get is every time you run IPFS bit swap want list, you'll get a small list of blocks that your peer is in the process of requesting. And if you run that multiple times, you'll actually get your want list updating as new blocks are downloaded and you no longer need them anymore. And so it gives you an idea of kind of this dynamic nature of bit swapping and requesting content. So we'll jump back to our slides here for a second. And again, you can run that a bunch of times to kind of get an intuition for what's going on as you're requesting content. And then, once that's done, or at the same time in a separate terminal, you can do things like we can ask the DHT for peers that are actually providing the video. And the way BitSwap works, it tries to be pretty clever about things. So for instance, if someone happens to be pinning or able to provide, say, the top level hash for a very large directory of bits of a video, then chances are they're probably also going to be able to provide the subcomponents, the sub-blocks of that video. So BitSwap takes advantage of that information to try and optimize how it actually gets data. So if you can find a peer that is hosting the full piece of that video, then chances are that peer can also provide the rest of the data. But that's not always the case, and the protocols don't assume that. You can also try to see, based on some peers that might pop up in that find providers call, you can see if we've actually downloaded from that particular peer. And so here on the slides, I actually have included my peer ID here. And so what you can do is you can query your own IPFS BitSwap ledger to see if you've downloaded data from my peer ID or from my peer. Because I happen to be hosting it, chances are you probably have. And so what would happen is you could run a command like this. And obviously, I am running my own peer here, so I probably haven't exchanged any data with myself. But you might see that you have multiple exchanges with my peer here, and you can see the number of bytes that have been sent and received, and the debt ratio. So that's just the idea of like how much content have you requested from me versus how much have you given to me. And depending on what your BitSwap strategy is, into account debt ratios and things like that, so that you don't just give away a bunch of information to peers that are just requesting information and not providing information or data. And then, of course, the whole way along, what we're actually doing is we're actually talking about or exchanging blocks of data. So at the end of the day, that's exactly what we're sharing. And we can explore one of the blocks from our want list. So as you're querying that want list, you can see that they'll pop up some various blocks. You can grab the hash from one of those block lists and see what they look like, and even directly download or get a particular block if you feel like it. But you can also so this was from a previous run of mine. I actually got this block hash come up. And so what you can do is query for that. And in this case, I say IPFS block stat, and I get the key and the size of that block. So this block is actually smaller than 256K. So there's no sub-blocks, and that's just a direct block that my node was querying to access it. It's a piece of that video puzzle, if you will. Okay. Now this brings us to another sort of aside where we'll talk again about IPLD very briefly. So for context, sitting on top of all of this bit swapping and peer finding, the core pieces of essentially this distributed data store, is the IPLD data structure, or the DAG data structure. And this is helping us to organize all of the linkages between these blocks. So we don't want to just go out and grab little bits and blocks here and there, but actually the blocks that are relevant for a particular file. So what chunks are associated with what file belongs in which directory, etc. And this is what provides a whole structure to the interplanetary file system that we're trying to interact with. So speaking of which, in our previous session, I mentioned in the homework or challenge section that you should try to figure out how to represent your JSON file as an IPLD DAG object. And maybe some of you tried this or played around with the DAG Explorer a little bit. For those of you who didn't, or who would like to see how you might do something like this, we'll take a quick look at a possible solution right now. And so again, this is a bit of an aside, but the reason I want to go over this is because it provides a pretty good intuition for how the DAG works. So the kind of goal today here is, can we build up a useful intuition for how data is exchanged between peers, how we find peers, and then how we actually represent the data that we're sharing among peers. So first things first, here's a link to the IPFS object, which you can look at in your browser like anything over a gateway. And then the second one is actually the IPLD Explorer, a link to IPLD Explorer to actually explore this particular DAG object. And then here is the code to actually generate a simple DAG object. So we're going to go through it really quickly, line by line. And if you have any questions along the way, don't hesitate to ask. Okay. So essentially, remember what we're trying to do here is we're trying to create a hierarchical data structure, essentially. And I do highly recommend that you copy and paste these lines so that you can get an intuition for what's going on. So we'll start by creating a base Unix file system style directory that's empty. So at the top there, base equals, and we just do IPFS object. All of these interactions are happening over the IPFS object API. So we're creating a new Unix file system style empty directory. And we're going to, and what happens is when you run that command, you get back a CID for that particular object. And so we assign that to the base variable so that we can reference it later. And then say we want to add a picture, right? We're trying to, in this case, we're actually trying to build up the JSON, essentially the JSON structure that we were using in our previous Đapp profile example. And here I'm using Lucas as the example, Lucas the dog. So we want to add his profile picture to IPFS. So IPFS add, and we'll add his profile, and we assign the CID to the pic variable. And then what we'll do is we'll update the base variable by going IPFS object patch the existing base CID, and we'll add a link, which we call pic, which links to the pic CID. So essentially what we're doing is we're adding a link to that, an IPLD link to the IPLD empty directory, okay? And then we're going to do the same thing for a couple of different items. So we'll add Lucas's first name. We'll add his last name. So we create a first and last variable. And we're going to create a subdirectory for those values. So we create a new subdirectory, IPFS object new Unix file system directory. We assign that to name. And then we recursively update that name directory by adding links to first and last name. Make sense so far? Then what we're going to do is update base again by adding the name subdirectory, or a link to the name subdirectory. And then finally, we'll add directly to that base level IPFS his biography. Okay, and it looks like I just got a question over on Slack, so let's jump over there very quickly. So the question is, the base hash value should have changed values when you patch it. And so the answer to that is yes, exactly. So because IPFS and IPLD objects are basically representing their underlying content, when you update the content, you get a new value back. So hence why we're doing this sort of recursive updating of base. We're reusing the base variable here. Question. So when we do something like this line here, we're saying, okay, let make base equal to the output of this command, IPFS object patch base add link name. And in fact, if you want to see kind of what's going on, you could run all of these lines of code, and then this last one doesn't assign anything to a variable. What it will do is output the CID of the final base object, and you can see that that's what's happening at each time we're sort of recursively reassigning the base or the name CID value. So if you go all the way down to the bottom here and run this line, you'll see that happening. So I'm going to actually jump over and do that right now so that you can, if you're following along at home, you can see how that looks. So here we go. And I'll jump back over here. And I just copied and pasted all of those lines in. They ran one by one. And so as we're updating it, what we get at the bottom here, when we run IPFS object patch base, and we add the link for bio, that last thing that we've done is we've updated that base, and we get a CID hash back. So if you take that hash and you go online, you'll be able to see the structure there. So in fact, if we come back to our presentation here, and we click on, say, the IPLD Explorer, you can then go and check out that particular file or object. And you can explore it online. So in fact, if you like, I'll do that with, I'll do that live right now. And we'll just jump back over to here and paste this hash. And we'll open up a new tab. There we go. There we go. Oops, doesn't look like that copied. Here we go. Beauty of live examples. There we go. So here we've got the file there. We've got the bio, which we can click on and see Lucas's bio. We've got the name, which we can explore down the DAG structure. And now, instead of just storing a link to an image file, we can actually store the image directly. Okay. Okay, so at this stage, I'm going to stop and see if there are any other questions or concerns along the way. So I'll just jump over onto the Slack channel very quickly to see if there's anything. And it looks like we've got a thumbs up on answering that question, so that's great. And there doesn't seem to be any audience questions on the Q&A link, so we can just keep going because we're running a little bit behind schedule here today. So the next little bit of the IPFS communication puzzle that I want to talk about is the relatively new publish-subscribe communication pattern that IPFS supports. And we're actually going to play around with this a little bit next week when we actually do some coding. I'm wrong. There is a question over on Slack. Let's just jump over there and take a quick look. So the question is, are each of these sub-values provided with their own hash? And so the answer to that question is yes. And then the next piece is, it would seem that the hash would be bigger than the respective value in a lot of cases. Also true. So when you're adding tiny little pieces of data to IPFS, you get a hash that could definitely, and in the case of Lucas's name, be larger than the actual data itself. So in some cases, if you're only using very small, so if you've got a lot of very small bits of data, then actually overall your data size could increase. However, what's happening, so overall, peers would have to download slightly more data. But what's actually happening really is you're just creating references to these things, and the DAG is really just representing references. If it's lots of very small data, that DAG structure, if you download the whole thing, would be slightly larger. But generally what you're going to do is just share the top level hash, and then you'll use bitswap to grab the little bits and pieces that you need. So it's not going to lead to a lot of data bloat, but it is something to think about in terms of when you're storing very small bits of data. For larger bits of data, obviously, a fixed size hash is quite a nice thing to have because it essentially bounds on how you're going to represent a given particular piece or particular sized file. And if you want me to elaborate a bit more on that, just let me know in the Slack channel there. Okay. So back quickly to the pubsub topic. So it's a pretty standard messaging pattern where publishers, they don't necessarily know who or if anyone is subscribed to a particular topic or category that they are announcing on. And subscribers, they only receive messages on a given topic that they're subscribed to. So it's a pretty simple concept where we have publishers publishing content or information or messages on a particular topic, and subscribers who are receiving those messages. The key feature here is that there's actually no direct connection necessarily between publishers and subscribers. Okay, so this makes for a pretty powerful communication system, and it's perfect for something like a distributed network of peers like this, where not everyone is connected to everyone else. Okay, so why am I showing this here? Well, because IPFS is actually starting to use pubsub and other mechanisms like it to speed up delivery of things like network notifications, and in particular IPNS networks. You may have noticed that updating your IPNS hash is quite slow. And so things like pubsub will actually allow you to disseminate those updates much more quickly over IPNS. And you get a much faster resolving of those hashes. To enable this, you can actually use it now. There's an additional flag that you'll have to run when you start up your IPFS daemon, and that is the enable namesys pubsub feature. And I do highly recommend that you use that because it does speed up IPNS resolving quite quickly. And we'll talk about another flag that you can enable in a little bit here. So you can do that. And then the long and the short of this really is that just pubsub allows for dynamic communication between peers that's fast, scalable, and it's wide open, which is really the goal of IPFS in the first place. Right now, IPFS uses something called floodsub, which is an implementation of pubsub that essentially just floods the network with messages. And then the peers are required to listen to the right messages based on their subscriptions and ignore everything else. So this is a sort of first pass, not maybe the most ideal one, but it works pretty well already. And we'll see next session that will actually take advantage of this a little bit. Soon, IPFS is going to take advantage of something called gossip pub, which is more like a proximity-aware sort of epidemic pubsub where peers communicate with proximal peers and they route messages through their neighbors essentially this way. So watch this space because it's going to be a pretty important part of sort of speeding up and scaling up the IPFS network in general. So the way this works is that messages are routed through connected subscribed peers. But what this means is that if peer A and B and C are all subscribed to a particular topic, say foo, and A is connected to B, and B is connected to C, but A is not directly connected to C, A will still receive messages that C publishes to foo through B. Right? So this is pretty useful for routing messages in networks where we have suboptimal connectivity, or peers are going in and out of connections. And there's a couple of commands. As always, there's a command for that. So you can see which pubsub channels you're connected to by going IPFS pubsub ls to list them. You can see which peers are engaging in pubsub by looking at IPFS pubsub peers. And then, more importantly, you can actually play around with pubsub directly from the command line. So what we can do is we can actually play around with it right now for anybody who happens to be following along live. So the first thing you'll need to do is you can always stop your daemon and restart it by just Command C or calling IPFS shutdown. And then you can fire your daemon back up as IPFS daemon and then just enable pubsub experiment to actually allow pubsub to operate. And then what you can do is you can make your peers subscribe to, for example, text topic if you'd like, or any particular topic you want to try. You could also create one that's more specific to your local machine for this particular test if you'd like, just so that you're not getting messages from all over the place. If you're subscribed to Textile test topic right now and you're sending messages, please send safe for work messages only. So what you can do is you can do IPFS pub sub, that sub command, and then you can subscribe to a particular topic. And then what will happen is your peer will just kind of sit there and will print out any topics or print out any messages as they come through. So what I'm going to do, and then so again, we're going to use a couple of different tabs. I'm going to start on this IPFS pubsub, and we're going to subscribe to this Textile test, and it's just going to sit there. Then what we'll do, is we'll jump on a different tab or a different terminal. And what we can do is send a message over there. So IPFS pubsub publish to the Textile test topic. How's things over on that other tab? So if we run that, nothing exciting happens here, but hopefully, live demo and all, we get our message over here. How's things over on that other tab? And so we can actually communicate between peers subscribed to a particular topic. So you can imagine if you're building an app system based on top of this, you could use pubsub to notify all of your peers that are running in your private swarm or whatever of some activity that might have happened, some update to the overall app system, a new, whatever your decentralized Twitter app is called, a new tweet goes out. You could use something like IPFS's pubsub to communicate that way. And so we'll play around with this idea in JavaScript code next session. All right, so feel free to play around with that yourself. And if you'd like, you can send me, I have this running for a bit, so you can send me some nice messages over IPFS. So we're pretty short on time, so I want to go through just a few key pieces of our example before I leave you to work on it over the next couple of days, and then we'll pick it back up in more detail on in our next session, which will be next Thursday. So first things first, make sure you have the Đapp from our last session. And so the easiest way to do that is you can just, if you haven't already, you can clone the Textile Đapp, and then you can just check out the profile demo branch. You can yarn install it, and then you can yarn watch it, and go to localhost on port 8000 to see the working Đapp. So that's our baseline. We're going to change a lot of it over the next couple of minutes and over the next couple of days working at home. But that's the baseline that we're going to be working on. And so our goal for coming out of today's session is that we're going to take our sort of static IPFS-based Dapp, and we're going to make it editable or dynamic. And so the first thing I want you to do is we're going to change how we interact with IPFS from the browser. And so last session, we used IPFS companion plus window.ipfs is required to enable some nice IPNS features. Okay. Right. Anyway, so now we're going to use something called IPFS API to interact with our local daemon directly instead. Okay, so we're going to actually directly interact with that local daemon. The reason for this is that, as I mentioned before, IPNS support in JS IPFS hasn't been released yet, although it's very close. And window.ipfs that we get through the IPFS companion doesn't let us publish to IPNS keys yet, also, or at all. Also, this just shows you another way to interact with an IPFS API, and so it's a good thing to have in your toolkit in the first place. So there are a couple requirements to get this working. First, you have to have your local daemon running, and we did that for the last session, so that's not all that different. The second is you'll need to be able to specify the port, etc., that your daemon is running on. And if you use the default, then you don't need to worry about that because the IPFS API package just uses smart defaults, and you're all good. The other thing that you'll probably need to enable is cross-origin requests for localhost, or cores for localhost. And so you can very easily add that to your IPFS, your local IPFS daemon, running these three commands here. And note, we're just adding it to localhost, so you're not at risk of any attacks from other sources. But you'll want to enable for your localhost, and then get some credentials and allow different methods for your HTTP header component of your API config. So that's pretty easy to set up, and I'll add a link at the end of these slides that shows you a link to a blog that talks about some of the config options for IPFS that you can explore on your own as well. Okay, so essentially, once we've done that, we'll restart our IPFS daemon, and we'll be able to connect to it from the browser. And this is essentially what our goal is for this week. So basically the same Dapp that we had before. Oh, I'm getting... oh, okay, sorry, it's back. Great. Just getting some feedback that the video had stalled, but it looks like we're back, so that's good. I'm not sure for how long it's been off, so I won't jump back, and I will fill anyone in that they might have missed on the Slack channel. But essentially, this is the goal for this week that we're going to try and achieve. So it's the same Dapp that we had before, except now we're going to make it possible for you to edit your entries. And so you'll see here I actually capitalize IO in 2 cases. So you'll be able to edit your bio and job titles and things like that, and then actually save those changes and republish them to IPNS, all from within a browser. And then you'll also be able to edit your photo if you'd like, so you can replace your image to use a different one. And this one's a little bit older, so I look a little bit different, but you kind of get the idea. So we'll enable these sort of dynamic updates, and what will happen is from the browser we'll actually update our actual IPNS published values. So there's a couple of things that we can do to get started. And again, we're running short on time. We did start a little bit late, so I'm going to go a little bit past 10 o'clock here. But now that we're adding some of this interactive features, things are starting to get a little bit more complicated with our particular Dapp. So our single page app is starting to look and feel a lot more like a real app. So what we're going to do is, to start with, we're going to throw in a real software architectural pattern known as model view view model. And we'll play around with this a little bit, but it's made very simple using this very nice knockout JS package, which we'll play around with a little bit as we learn a little bit more about this. So that brings us to another aside, not quite an aside because we're actually going to use this, but MVVM, basically it facilitates separation of developing the graphical user interface, so our view, from the development of the actual business logic of our Đapp, our data model. And in our case, our data model is literally our JSON structure that represents our actual user profile. That is our data model. And so with this MVVM setup, we're going to introduce the concept of a view model in the middle of our view, our GUI, or in the case of a web page, single page web app like we have, our markup, and our actual data model, which is our underlying JSON data. We've got this view model that's going to control basically how the view is exposed according to the underlying data. So now the new role of our markup is really just to bind the data exposed by our view model to actual visual components. And that's where knockout JS comes into the picture, and I'll show you how to do that in a second. The reason we're doing this is, well, one, I'm trying to introduce various different programming modes to show you how these all these different distributed web and IPFS APIs fit into your existing application development frameworks, but also because it gives us a nice declarative style that gives us some nice features like automatic UI and data model updates, dependency tracking between user interface elements, and a more clear separation of concerns from visual elements to the actual business logic of interacting with IPFS. Right? Because what we essentially want is we want an app or a Đapp that looks and feels just like any other on the web, and in the background is interacting with IPFS and the distributed web in a very sort of nice, transparent, but easily abstracted way. So we're actually introducing some different dependencies here. You don't need say the queue window.ipfs fallback or window.ipfs is required anymore. But what we will add is knockout mapping, and IPFS API. And so the way to do that is actually, I've created another branch, which you can check out by going to git checkout build profile example -mvvm. And that's a new branch that has all of this stuff in it already. But of course, if you're working with a web app from Node, you can always do yarn add knockout or npm install knockout, or however your sort of favorite way to add to your package.json file might be, even manually if you like. So we've got a few different dependencies. And I'm going to actually go through all of the different changes in a moment with you online. But first things first, the simplest thing we need to get our app up and running is these new packages and the content that's available at this gist online. And so I will take you there in a second, and we'll go through just some very simple example. And then I'll kind of unleash you onto the wild, and you can play around with it yourself. And I'll be sitting on the Slack channel where you can ask questions as we go along. So should be able to access the slides here. Here we go. So here's a gist. This is some code snippets for our IPFS Đapp example. And there's really only a few things that we're going to actually have to update here. So most of this index.html that we had from before is pretty much the same. what we've done is we've added a few binding elements to our MVVM model view. And so we'll jump down here first, and this is the main.js. It's actually simpler, i.e. less code, than our previous example. And this is just to get the MVVM stuff working. So it's a very similar setup function. You can copy and paste this to replace your old main.js, and you can copy and paste this to replace your old index.html and restart the Đapp locally, and it should just work right away, assuming you've installed those other packages. Again, probably the easiest thing to do is to check out that MVVM branch and then just copy and paste these in to replace the main and index files. Having said that, we can just go through here very quickly. So we're getting a reference to the IPFS API, very similar to before. All this code is exactly the same as we had before, where we actually go, we resolve the IPNS hash of the local IPFS ID. We go out, we get the actual file, we convert it to a string, we parse it into JSON, and in the previous example, that we then went into a new function and we actually populated the UI elements. Now, instead, what we're going to do is we're just going to set up a view model based on this JSON structure. Right? So we just feed, this is ko knockout.mapping.fromJS. We give it the JSON, and that automatically populates a view model for us. Then what we do is we apply the default view model bindings, ko.apply bindings to the view model. And I happen to add a nice little spinner in there so that we got some feedback if when the application was loading, but you don't really need to worry too much about that. And lo and behold, we have a nice, pretty looking Đapp. The only other piece we need to get that to work is we edit the index.html file. So now we had before all of our different stubs for our different values. Now we've just added a few components to bind the data from our view model to the actual components. And I highly recommend you jump onto, and there's a link for it at the end of these slides, to the Knockout.js website. They actually have some great tutorials to give you an intuition for how this is all working. It's definitely a great way to accelerate single-page Đapp development, and I highly recommend that you play around with a little bit. And again, I'll be standing by with any questions that you might have. But the idea here is that we can actually bind data elements to visual objects on our Đapp. So for instance, if in our profile here, we have our username, or our name, as a level 1 header. And what we can do is we can bind the text for a span to name.first in our JSON data model. And we can bind the text of a span to name.last to get our first and last name. And similarly, we can add in our work titles, and we can add in our social media links. And we can actually bind to a whole array of work-based information and a whole array of social media links. And Knockout.js gives us this for each bind object so that we can actually loop through an array of values and assign specific features. Okay, so it's kind of hard to see exactly what's going on just by looking at some code here. So what we can do is we jump back over to this Đapp, and when we refresh it, get the spinner, and then our app loads up, and it looks exactly the same as our app before. But if you look at the source code, for instance, and I'm doing that now, you'll want to do it on your own machine so that you can see what's going on. You can actually see that it's using this MVVM style explanation, or MVVM pattern to actually display this. So we've got an identical app with fewer actual lines of code. And then the next step there is to then take that and start adding some interaction between the UI elements and the view model. So if we jump back to our presentation here, There's a couple of slides that try to help to explain what exactly is going on and how you might want to approach actually playing through the examples. And you can pass through here, and this sort of gives you an idea of what you should go and look at line by line. And then there's a link at the bottom here to the GitHub diff so that you can see the changes that are made to our last app. So for instance, if you scroll down here, we can see the new packages that were added. You can see the changes that were added to our index.html file. And then more importantly, you can see all of the different code that was added to enable interactive or editing for our Đapp, right? And then you've already seen the changes that were added here, which are pretty minimal. So play around with that. Make sure that you can at least check out that branch and get it running okay. And then next week our next session, we'll play around with this a little bit more, and we'll break down the individual pieces a little bit better. In particular, focus on things like handling the data update, where we'll actually add a file and then publish it over IPNS, just like we do locally. All right, so I'm going to leave you with this stuff for the next couple of days, and then we'll return to this when we meet again next session. So a quick summary of what we've kind of got now is we've got a decentralized app that supports structured user profile information. And we will, by the end of this week, have the means to edit the profile information in a user-friendly way. And hopefully we've created a look and feel that doesn't scream a sort of clunky decentralized app, but actually looks and feels a lot more like a normal app that you might see on the centralized web. So what we probably want next is some sort of authentication and encryption, additional profile options, maybe some social media sharing options, things like that. And by the end of this session, we'll have added a few of those features to our Đapp so that you have something that sort of works and makes sense in how apps work these days. So that's it for today. Here are a couple challenges that you might want to think about as you're playing around with this. Here are some additional resources, and I'll add a few more links that I mentioned along the way at the end here for you to play around with. Okay, so thanks again for joining us live, and we'll see you next session, which is next Thursday at 9 a.m. Pacific time.